of the most notable applications of the moment of inertia is how it affects the speed of a rolling object. So one of the common problems that we've looked at before is a sliding box on a frictionless surface, and then see how it slides down an incline. So we can use energy conservation to find the velocity at the end of the slide. It's kind of a classic problem, right? Hopefully you remember it. It might have bothered you that we always talked about sliding objects. Why don't we talk about rolling objects, right? A wheel is great. As the wheel rolls, there is virtually no friction slowing down the rolling object, so why not just use a rolling object instead of a sliding box on a frictionless surface? That's a pretty unrealistic kind of thing. Well, the reason is that there is energy stored in making the object roll. So that means that there is a rotational kinetic energy. So when the ball rolls down a hill, some of the potential energy is converted into rotational kinetic energy, while some of the potential energy is converted into translational kinetic energy. So translational kinetic energy here is what we usually think of when we talk about kinetic energy. So it's 1/2 mass times the velocity of the center of mass squared, where the velocity is the center of the mass of our object. Okay, so anyhow, it takes energy to make the object roll, so that means that the more energy it takes to make the object roll, then the less energy there is for translational kinetic energy, and the slower the object moves. So our total kinetic energy is equal to the sum of the translational kinetic energy and the rotational kinetic energy. We know the translational kinetic energy, that's 1/2 mv squared, and the rotational kinetic energy is similar. It's 1/2 times I, the moment of inertia, times omega, the angular velocity squared. Remember, the angular velocity times the radius is equal to the velocity, so if the rotating object is not slipping, the omega is equal to the velocity divided by the radius. When we square this, we get velocity squared over radius squared. That means our rotational kinetic energy is now beta times 1/2 mv squared, and because the r squared in the moment of inertia canceled the r squared from the angular velocity, so we just have beta 1/2 mv squared. That means that the total energy is 1 plus beta times 1/2 mv squared. That means the larger the beta, the larger the proportion of the kinetic energy is in rotational kinetic energy, and the smaller the translational kinetic energy, assuming you've got different things with the same amount of kinetic energy. So if the objects have the same total amount of kinetic energy, the larger the beta, then the slower the object will roll. In our example here, let's say we have 42 joules of kinetic energy, and they're put into a series of objects. In the case of a ring, the beta is 1, so that means 21 joules are in the translational kinetic energy, and 21 joules are in rotational kinetic energy. In the case of a cylinder or a disk, beta is 1/2, so in that case 28 joules will be in translational kinetic energy, and 14 joules will be in rotational kinetic energy. So the disk or the cylinder is going to move a little bit faster than the ring. So in the solid sphere, the beta is 2/5, so in that case 30 joules will be in translational kinetic energy, and 12 joules will be in rotational kinetic energy. So if we roll our objects down the hill, the sphere is going to roll the fastest, and the ring will roll the slowest. So if we want to calculate the velocity of a rolling object after it has rolled down a certain distance, we can solve this exactly the same way we did before, but now we need to include the rotational kinetic energy. The change in kinetic energy is 1 plus beta times 1/2 mv squared, and the decrease in potential energy is mgh. So if we set those equal to each other, because all of your potential energy is going to be converted into kinetic energy, that means that after a height h, all of your potential energy is converted into kinetic, and you're going to get 1 plus beta times velocity squared is equal to gh, since our masses have canceled. Solving for velocity means that if you divide by 1 plus beta and take the square root, to get the velocity is equal to the square root of 2 times g times h divided by 1 plus beta. Notice if the object isn't rolling, then the beta becomes 0, and this just becomes the old equation, v is equal to the square root of 2gh. Also notice that the changes in the center of mass, which is why we're giving here an h sub cm here. It's not centimeters, it's center of mass. So the idea is that the velocity is inversely proportional to the square root of the beta, where essentially the larger the beta, the smaller the velocity. So we can also do the reverse problem. So if an object is rolling on the ground, and then it rolls up an incline, then the question is, when does a rolling object roll higher up the hill or lower up the hill? In this case, the velocity of the objects are the same, and that means that the object that has the largest beta, well, it's going to be carrying the most kinetic energy, so that means it's going to go higher up the hill. So we have a question here. If we have a block sliding along a frictionless surface and a ball rolling along the same surface, and they both start to move up an incline, which will go to a higher height, assuming that they are both moving at exactly the same velocity. Well, the one with the most initial kinetic energy will go the highest. Remember, if an object is rolling, it has both translational and kinetic energy, and rotational kinetic energy. So that means it takes energy to make the object rotate. So the rolling ball is going to have more total kinetic energy than the sliding box, because the rolling ball is going to have translational kinetic energy and rotational kinetic energy, while the box is just going to have the regular translational kinetic energy. So that means if the ball has more kinetic energy, despite the fact they're going at the same velocity, then the ball is going to roll higher up the hill than the box, and that's because it's got this additional energy in the rolling. So one way of thinking about this is that it takes a certain amount of energy to make the object roll, so then basically it then rolls up the hill a larger distance. Okay, so this is probably a little more than we need here, but this breaks down quantitatively our situation where we're rolling an object up the hill. So the change in potential energy is mgh, right? We're going up the hill, so potential energy will increase. And the change in kinetic energy is minus 1 plus beta times 1/2 mv squared. If we do the algebra on this, we get the height is equal to 1 plus beta times the initial velocity squared divided by 2g. So that means if the velocity is held constant, the larger the beta, the higher up the slope the object rolls, and the smaller the beta, then the lower up the slope it goes. Okay, so you have some questions to answer about this. Also, I've put up a FET from O-Physics that looks at some different shapes as they roll down an incline. Good luck.